So in previous videos, I went over some examples on linear independence and dependence after introducing the topic linear independence and dependence. So now what I'm going to do is I'm going to do some proofs regarding linear independence and dependence. So the first proof is that we have a set S, which is a subset of the m by n vector space. In other words, we have a subset that contains matrices of a certain dimension. And given that S, that this set here is linearly independent, we are to show that the set A1t, A2t, AKT is also independent. So basically what the set is just the transpose of the set S. Okay, so this is assuming that you know what a transpose is. So if you don't, well, just a quick reminder. So a transpose is done by sort of switching. Is done by switching the first row of the matrix with its first column, and then so on and so on. So you switch the second row with the second column, the third row with the third column, and you do this. So do this k times. Where the dimension, well, you do this a certain amount of times depending on the dimension of your matrix. So that's just a quick reminder of the transpose. For example, if my matrix is 1 0 0 1 0 0 0 1 0, then A transpose, what you'll do is you'll take the first row and switch it with the first column, right? So you take the first row, switch it with the first column. And you take the second row and switch it with the second column. So you'll have 1 0 0 0 1 0. So if you start with swapping rows, then you need to be consistent. So I swap the first row with the first column, and so I do the same for the second row with the same column. So that's what you need to know for transposes. Even though we're not actually going to handle a lot of transpose algebra in here, it's just to remind you what the transpose does. Okay, so now let's start the proof. So we start the proof by saying that if S is linearly independent, then by definition of linear independence, then that means that we can express this set over here as a linear combination where we have C1A1 plus C2A2 plus ... plus CKAK equals, in this case, the zero vector is, in fact, so this is the zero matrix. So this is the zero matrix with a certain dimension. We don't know what the dimension is, and in this case, it doesn't really matter. But we just know this part, and we also know because it's linearly independent, we know that C1 is equal to C2 is equal to C3 is equal to, and so on until CK, and all of those are equal 0. So all of my scalars are equal to 0. So there's 0 scalars, because that's the definition of linear independence. So now what we do is we want to get to this set, right? So what we can do is we can take the transpose, we can transpose both sides, okay? So take the transpose on both sides. Take the transpose on both sides. So we have C1A1 plus C2A2 plus ... plus CK AK transpose, and I'll also transpose the zero vector, right? So remember that the zero vector in this case is just the zero matrix, okay? Now, you need to remember something else from transposes. So one of the properties of transposes, is that A plus B transpose is equal to A transpose plus B transpose. And this can be applied for as many matrices inside the parentheses as you want. So you can have A1 plus A2 plus plus AN, and N can be so it can be any number of matrices inside the parentheses, sorry. But if you take the transpose, then automatically, by a property of matrices, you can write A1 transpose plus A2 transpose plus AN transpose. Okay, so that's just the property of transposes. So that's what we're going to do on the left-hand side. So we're going to write C1 A1 transpose plus C2 A2 transpose plus plus CK AK transpose. And taking the transpose of the zero matrix just gives you the zero matrix. So we still have the zero vector on the right hand side. So now another property of the transpose is that if we have a scalar C, so C belongs to R, and a matrix A, and when we take the transpose, then we can actually take the scalar out and it won't affect the result. So that's equal to CAT. So this is another property of the transpose. So we can apply this to the left-hand side, and we have C1AT, A1T plus C2 A2T plus C3A3T plus plus CK AKT is equal to the zero vector, or in this case, the zero matrix. So what do we have here? Well, we actually got our set, the set that we were looking for, which is, so we're looking for this set, right? We're trying to look for this set, and we do have that. We have A1 transpose, A2 transpose, AK transpose. And remember what we were trying to look for? We were trying to look for linear independence. So for this thing to be linear independent, for this to be linear independent, C1 needs to be equal to 0, C2 needs to be equal to 0, and so on until CK equals 0, right? But we have this because we said in our assumption, it's given that S is linearly independent. So that means that C1 equals C2 equals equals CK equals 0. That means that each of these scalars are 0. So these are all 0 scalars, which means that all of these scalars, because we haven't touched them, they're the same scalars. So these scalars are still the same, and they're all still 0. So since S was initially linearly independent, C1 is equal to C2 is equal to is equal to CK is equal to 0. So we basically have the trivial solution. So we have the trivial solution for the set A1 to A K all transpose, meaning that this set is linearly independent. So we've shown that this set is linearly independent since initially S is linearly independent, and using properties of transpose, so using this property and that property of transposes, we conclude that for this equation, we get the trivial solution. And since automatically when you get the trivial solution for an equation like this, automatically by definition of linearly independent, you can say that this set over here is linearly independent. So that was one proof regarding linear independence and dependence, and I'll be doing another one.